This presentation is delivered by the Stanford Center for Professional Development.
All right, let's get started. So today, video segment is about a small device called the Hummingbird. The Hummingbird was developed at IBM Watson Research Center in the early 90s, and it was published in the Proceedings of ICRA 1992.
The Hummingbird Mini Positioner is a compact device designed for the ultra-high-speed positioning of low-mass payloads. Developed for the contact and non-contact probing of planar objects, it can probe at over 50 cycles per second, with accelerations exceeding 50 Gs. The 5-bar linkage of the Mini Positioner covers a 13mm square workspace. To reach larger regions, the entire Mini Positioner can be moved. The two main links are driven by high-performance moving coil actuators, and the link positions are sensed by low-mass optical encoders. Preloaded bearing pairs at the joints provide high stiffness and zero backlash for accurate XY positioning, and a miniature linear servo motor provides 1 millimeter of Z-axis travel. The Hummingbird system can generate peak accelerations of 50 to 100 Gs in all three axes. To avoid shaking the structure holding the Mini Positioner, the mechanism is designed to be reactionless during XY motion. The dynamically balanced linkage assembly generates no net XY reaction forces during motion because the net center of gravity of the moving parts remains fixed for all linkage orientations. The net Z-axis reaction torque generated by the two link actuators is actively cancelled by a third rotary actuator, which oscillates only very slightly because of its high rotary inertia. One of many applications for high-speed probing is the electrical testing of high-density circuit boards. When driven by a custom multi-transputer servo controller, the Hummingbird can provide such testing at unprecedented rates. At 40 tests per second, as shown here, the camera and the human eye are unable to follow the probe motion. The use of a strobe light, however, reveals the three large XY moves and the small Z moves in this repetitive pattern. Here, a pattern of smaller moves on a 225 micron grid is being demonstrated at only 10 tests per second. Two quadrants of the grid are probed systematically, while the other quadrants are probed only partially but more randomly. Here, that same pattern is being probed at 20 tests per second. And finally, the complete 372 move pattern is performed at a full 50 tests per second. Details of the motion are shown in the high-speed video being replayed 33 times slower than real time. Each probing cycle includes one XY and two Z moves and takes only 20 milliseconds to complete, yielding a total of 150 distinct moves per second. At this speed, the XY probe placement accuracy is approximately 5 microns. To provide a more familiar size reference, the probe is shown here above some ordinary table salt. The Hummingbird was programmed to contact each of 3 selected grains at 49 different locations at a rate of 50 probes per second. The inset shows one of the salt grains after probing and the characters formed by the tip. The letters are about 140 microns tall, with a typical dot spacing of 20 microns. The Hummingbird Mini Positioner resulted from the interdisciplinary team effort of these and many other contributors.
So, unbelievable, huh? Well, obviously, when you want to move very fast, you have to make everything very light in order to achieve that. If you have moving structure, it's going to be impossible to do it. And now integrating all that structure in a way where you can get all the stiffness, avoid vibration, is not a simple problem. Okay, well, today's lecture really now is going to take what we have learned about the frame assignment, the descriptions, and take these to a manipulator. What we're going to do is we're going to take this manipulator and start by looking at a link and try to see how we define this link. And from that description, we're going to introduce these promised description I mentioned earlier, the DH parameters, or the denavit-hartenberg notation, that would allow us to describe the link and its connections to the next or previous link. This is going to allow us to then precisely define the frames that are going to move with the links, but that will also allow us to connect the base through the structure to the end effector. So that will give us the forward kinematics. The forward kinematics is this relationship between the lost frame and the base frame. You remember we talked about this end effector placed at some location in space, connected through those links to the base. So if we have a frame here, if we have a frame at the end effector, these two rigid objects, in between you have all these links, and all of them are moving. And the question is, how are we going to define those frames? How are we going to attach frames to the different links? Obviously, you can go to each of the link and say, okay, I'm going to go to the center of mass of the link and put a frame. And you still have freedom in assigning that frame, but that would be fine. Then you will have to find the relationship between frame on the base, link one with your selected frame, and the next frame and the next frame. So if you think about it, let's say I'm going to put frames at the center of mass. So this is just one example. What is going to happen in terms of the relationship between two successive frames? How many parameters we're going to need to describe these two frames? Any idea? Well, you have frame, another frame. You have a homogeneous transformation. How many parameters? 6. All right. Now, this link, we know it moves just with 1 degree of freedom. And there are restrictions, right? So if we just go and place frames arbitrarily at the center of mass or any other point, we're not going to take really advantage of the fact that there is some set of constraints associated with this mechanism. So the purpose of what we're going to do is really to take advantage of those constraints and come up with a minimal description that allow us to somehow emphasize this variable, this joint variable that is rotating, and have it explicitly in the description. So what we're going to do, we will start with the link description, and then we take a look at the link connection, and from there we will identify those parameters and we will identify the variable. Some of the parameters are fixed. The length of the link is fixed. The relationship between axes, so if we think about axis I and axis I minus 1, there is some fixed relationships between them, right? As we move these axes, there are some parameters that are constant. What kind of parameters are constant there? What do you see as constant between these two axes?
Distance.
Hmm?
The distance.
Distance. So basically, these axes are maintaining a distance, right? And in general, these axes are not parallel, so there is a tilt between them, and that tilt is going to be maintained. And there are some offsets that will be introduced. There is an angle that is taking place, but we cannot see it with just the axis. We need to assign the frame, and we will start to see that relationship. So the link description, I'm going to take two axes and arbitrary axes so that we will not just take the parallel axis case. So axis I minus 1 and axis I are connected somehow through this link. So if we take a link, at the extremities of the link we have the joint axes. Okay. So what are the things that are constant? So you said distance. How are we going to define the distance between two axes? Come on, faster.
Perpendicular.
So perpendicular to a plane, perpendicular to an axis, but we have two axes. So it is a common perpendicular, right? Something that is perpendicular to both. That would measure that distance. So if we take this common perpendicular to both axes, then we have a sort of, I mean, this is going to be unique, right? Except if the axes are parallel, then you have infinite way of placing that common perpendicular. Okay, you agree with that selection? That makes sense. We take the common perpendicular, and that will give us this distance. So we call it A. So now you have to pay attention to the notation, because we're going to describe link I minus 1 with the parameter I minus 1, which is the common perpendicular to those two axes. So I minus 1 is the common perpendicular between axis I minus 1 and I. All right. What else we need to introduce? So if I slide axis I along this common perpendicular and I come to the intersection, there will be an angle, a twist angle. This angle, you see it? We slide it up to the intersection and there will be an angle. We call it the link twist. And it is the parameter alpha I minus 1, which measures this angle. And what we will do is we measure the angle along the vector ai minus 1 in the right-hand sense. And you're going to learn how to use your, everyone knows how to measure the angle in the right-hand sense? Okay. Just make sure you use your right hand, not left. It happens. Okay, so we have two parameters. In fact, we're going to see that in total we need 4 parameters. One of them is variable, the joint angle, or the joint displacement if it's a prismatic joint. And now we identify 2. Alpha and A are constant all the time. So once you design your robot, these alphas, alpha 0, alpha 1 to alpha n, are going to be constant. The same for A. Now, if we look at most mechanisms, we're going to see that the axes are not always apart. Most of the time they are parallel, and sometimes they are intersecting. So if we take the Puma, you have this first joint axis, and then you have the second one, and they are intersecting. If you take the wrist, you have 3 intersecting axes. So when we have intersecting axes, the question is, what is the common normal? So you have this axis intersecting here. Where is the common normal? So we take the plane formed by I minus 1 and I, and take a perpendicular to that plane, and that will be a vector perpendicular to both axes. Which direction? So we have this angle, but how we define it? Because I can take a vector in the plane or out of the plane, and that changes the direction of the angle. So we have sort of a free variable here to decide in which direction we're going to select alpha. Typically what we do is you have the base and you're moving toward the end effector. So you are putting this A, the vector A, you are pointing the A towards the end effector. So it is very intuitive to create those vectors. And once you have A defined, then you will be able to say, well, A is in that direction, and now I take the angle in the right-hand side. Or if it is in this direction, you will take it in the other direction. OK? That's for alpha. Now, what we're going to do next is to connect those links. So we defined the link through these two axes, the distance between them, the common normal, and the twist. But if we move further, we're going to have another link. Now, that other link will have another common normal, right? And this common normal will be between axis I and axis I plus 1. So that common normal will intersect with axis I, right? It intersects at some location with axis I. So we know this point where we have this intersection. Now, what we need to do is to introduce these two other parameters that defines those connections. And obviously, this is perpendicular to the axis I. So I don't know if you see this vector. How can you define this vector with respect to this line, A? That is, I use this color. Can you see it? You see this? This vector? You see it? OK. And you see this vector? What are the variables that we need to introduce to define it?
So you need the angle between the two.
Yeah, there is an angle between the two. That's correct. And this angle can be found if we slide this vector to the plane. We will find it. This is going to be, so when the link, that following link is rotating, we will see this axis rotating with it, and that angle increases and decreases. And there is one more parameter, which is the distance, this offset. So what we will do is we will project this vector on that intersection point, and then we can measure the distance, di. And now you can see the angle. So di is defined as the link offset, and this di is going to be constant for revolute joints. But for prismatic joints, it's really the direction along which the joint is going to affect the motion of the following link. So di will be variable if the joint is prismatic. So for a revolute joint, theta is the variable. So if, like in this figure, this is a revolute joint, as in here, this theta will be the variable. So theta I is called the joint angle, and it's variable for revolute joints. Basically, now we have everything that we need for each of the links. And if we identify alpha, A, D, and theta, we will be able to go from one frame to the next as we attach frames here, frames there, and propagate. So here is a short movie segment. If we could put the light a little bit off, please lower the light. So we have this manipulator, and it was designed to show you different properties about different angles. And you see the end effector moving, carrying an object. So we see axis of joint 2, joint 3, 4, 5, 6. So you have all these axes of rotation, and now the last joint. So let's go back to the beginning. So we have one axis here, we have another axis there, and you see this distance, this common normal. Do you see it? This is the common normal. So as we move, this is fixed, but basically and this is the angle between the axes. So what we're going to do is along this first axis, we're going to attach a frame. We will see that in more details. And along the x direction, along the common normal, we put the x-axis. So now here is a case of common normal between two parallel axes. There are many, many possibilities, but we are not going to make the commitment of the assignment until we place the next joint. You see, there is this point, and we do not want to introduce this road, so we will move the common normal there. So these are the rules that we will see in our frame assignment. Now that we decided this, that will decide the rest. And little by little, we build that structure that would allow us to do the frame assignment. So now we are assigning the frames, and the frames are assigned along the z-axis, most of the time at the intersection between axes or along the common normals. So this is the frame assigned here for this joint, and when we rotate the next joint, you have this angle, so you have another frame. When you rotate about this, so all these frames are assigned with the same origin. This is the three intersecting axes. You see that? Now, there is always an additional frame that goes for the object, and often we assign it depending on the task or the need. So you end up with a structure like this, basically these frames, and each of them is rotating just with one variable. And from there, you can go and then build your connection from the base to the end effector. And as your end effector is moving, it's covering the space. So in the just coming here, you can start to see the workspace of the robot. This is what we call the workspace of the robot, the space where the end effector can be positioned, given the joint limits, given the structure of the robot. There are areas inside of this that will not be reachable because there are joint limits on the different joints, and you cannot be able to access all these points. So the workspace is this volume of the space where we can position the end effector, and we will discuss this later more precisely about the definitions of the workspace. But this is basically what is going to happen in terms of how you define the workspace, where are these configurations that are not reachable because of the joint limits and because of the different length you have on your structure. So this is an example of the workspace that we need to study in order to position the base of the robot so that the end effector of the robot can reach in different areas. Okay. Let's go back to the links. So now that we discussed those intermediate links and their connections, we need to be a little bit concerned about how we define the beginning of the structure, that is the frame attached to the base, and how we deal also with the last links. And there is a lot of freedom there. This freedom comes from the fact that those frames can be assigned and moved as long as you are able to find a frame that is fixed with respect to that rigid body. So we saw that for axis I plus 1, we are taking the common normals, we are taking those twist angles. And if we think about it, this AI and alpha I are depending on I and I plus 1. So when we say AI, the definition of AI and alpha I is going to depend on axis I and axis I plus 1, which means that from 1 to n, having those axes will determine A1 to an minus 1 and alpha 1 to alpha n minus 1. Then now we have to somehow decide about what is A0 and An, what is alpha 0 and alpha n. And that comes from the way we define the frame attached to the last link and the first link. So there are many different conventions, and those conventions can vary following your task and requirement. But essentially what we try to do is to carry in the forward kinematics the maximum number of 0 parameters. Because when you put an alpha angle of 30 or 40 or whatever, you need to compute the cosine and sine, and that introduces more constants. So what you need to do is to try to select your frame in a way that makes A0, An equal to 0. That will simplify the forward kinematics. Alpha 0 and alpha n to be equal to 0. And we can do it here. So this is axis 1, and we have axis 2 and 3, etc. So for axis 0 is essentially connected to the base. It's fixed with respect to the base. But it has a freedom of being defined. So what you can do is you can move this axis and make it parallel to axis 1. And you can even make it coincident with axis 1. And now you can, by putting them along the same axis, you are setting A0 and alpha 0 to 0. So that simplifies the number of parameters you're carrying in your forward kinematics. Obviously, you might need a different frame, but that different frame can be computed with respect to this frame that you are introducing by a constant transformation, and you can do that separately. You don't have to carry it in the forward kinematics. So for the end effector, the problem of the end effector is that your end effector is doing many different things. You are carrying a tool, and now you need to compute the forward kinematics to this point. Your tool can change. You are carrying just this, and your task is to control this point. Or you're carrying a glass, and your description is really related to this object. So ultimately, you will need an imposed frame by the task itself. But in the forward kinematics, the frame n can be simply, most of the time, can be obtained simply by going to the intersection point associated with the wrist. And there you get the simplest form of that description. Well, this is not all the time the case. I mean, sometimes we give you, specify, well, I need this frame, and I want you to find that transformation to that frame. So you can do it that way. But in general, this frame that is associated with the tool, with origin ON plus 1, that is frame n plus 1, can be arbitrarily placed with respect to that last rigid body. And it depends on the tool you're carrying or the object you're handling. So for the last link, that is for frame n and axis n, what we're going to do is we're going to remove this frame in the same way and make it coincident with axis n, which means that we will have an and alpha n equal to 0. And that simplifies, again, the forward kinematics. So this is the summary, that we are really moving all these frames, and we are putting the frames for alpha and a, the first one and the last one, to 0. We still have to decide also about the theta and the d, because theta I and di depend on I minus 1 and I. And that means essentially that now we define theta 2 to theta n minus 1 and d2 to dn minus 1. So we still have theta 1, d1, theta n, and dn, and those will be fixed once we decide those other axes. So the convention again is, so you remember theta I and di, one of the two is constant. Theta I could be the variable. The angle theta n will be the variable if it is a revolute joint. So in that case, di is constant, dn basically. So what you want to do is to set the constant parameter theta I or di to be 0. The variable has to be variable. So that means if the variable is d1, then we make theta 1. If the variable is d1, we make theta 1 equal to 0. And if theta is the variable, we make d1 equal to 0. So here is an example for the first link. What we will do is we selected the axis, we reduced those parameters alpha and a, but now what we will do, we will move the point that will become the origin of the frame, we will move it to the same point of the intersection, reducing this d1, so there is no more d1, and d1 becomes 0. So this is by moving the axis, or actually orienting that axis so to make theta 1 equal to 0. For the last link, we are going to do the same thing. We are going to reduce alpha and a and make the selection of the point of that axis to reduce either dn or theta n by selecting the direction of that last frame. Because the last frame associated with that virtual axis n plus 1 is not yet defined. So when you define it, you define that axis. So the result is dn or theta n becomes equal to 0. So with this convention and those 4 parameters, now we can essentially, basically we defined the DH parameters, because the denavit-hartenberg parameters are in fact those 4 parameters that we just saw. That is alpha I, ai, di, and theta I. You have 4 parameters defining each of the links, and each of 3 of those parameters are going to be constant. 1 of them is variable. So in the case of prismatic joint, theta I will be the variable. In the case of revolute joint, di will be the variable. The first parameter, d1, will be set to, if we have a revolute joint, d1 will be set to what? 0. If it is a prismatic joint, theta 1 will be set to 0. The same thing for dn by the type of the joint. So, as I said, 3 fixed link parameters and 1 joint variable. And this variable is either theta I or di. Theta I for the revolute case and di for the prismatic case. So, as we said, the first 2 of those parameters, alpha and a, are describing the link, because we have the link and we have the 2 axes. And the distance, AI, the alpha II, describe that link. What about the d and theta? What do they do?
Describe the joint.
Basically describe how a link is connected to the next one. So you have one link, and D would give you this translation between them. If this is a prismatic joint, you have one link, you have the other link, and you are describing the translation through D. If it is a revolute link, it is going to be this angle. So DI and theta I describe the link's connection. That is, we go from one link to the next, and how we connect them, it is really through this DI or theta I. One of them is variable. Okay. Now you know the DH parameters? Good. So actually, our task, and probably the homework, will involve computing, finding these DH parameters. So you take a link, and you go and find alpha I, AI, DI, theta I, and you go through all the links. And once you have them, basically, you need to use them to compute your transformation. So we need somehow to use those parameters in our definition of the frames that we are going to attach, so that when we go from one frame to the next, we are able to describe the relationship using those parameters. So the frame attachment is a very, I mean, it will become for you very simple once you did a few examples. But it's very important, because the way you attach your frames, you will simplify or make it more complex. And we are going to very carefully look at this problem and make sure that as we attach the frame, we are going to use these parameters in the homogeneous transformation describing the relationship between two successive frames. And then we will be able to have that transformation, and then we propagate transformations, and we can compute the end effector with respect to the base frame by multiplying out all these homogeneous transformations. So how do we proceed with the frame attachment? Any help? What should we do? Where should we start? Okay, take a look. Frames. What is a frame? What is the most critical thing about the frame? Origin. Someone said origin. So we really need to decide a rule about how we select the origin of those frames. And we also need to decide something about the axis, right? A frame is the origin and the axis. So you have X, Y, and Z. And I have to make some decision also about the axis. So any good idea? What selection you would do for your x-axis or y-axis or z-axis? What convention you're going to? You need to do something systematic. So if you noticed what we did, we selected I-1 and I, and we said these are the axes, and we are looking at the distance between them and the offset between them. So these axes has a very important role. You want your frame to be aligned with those axes, right? So you want these joint axes to be the axis that define your one of the vectors, basically, x, y, or z. So let's quickly pick one, x, y, or z. Which one? Okay, now all together. Z, yes. So what we will do is, it's very simple. You have, I mean, you built your mechanism, you designed it. Now you have joint axis. Just along this axis, I'm going to pick the z-axis. All right. So we already made a big decision that if we pick the z-axis, now the rest. I mean, once you pick the z-axis and if you pick the x-axis, their intersection is the origin, or if you think about where the origin has to be, then you have a little bit of freedom, but basically you're almost done. So the z-axis along the joint angle is very interesting. Why? Because later, when you are going to rotate, for instance, about a joint, immediately you measure the angle theta about that axis, and that is your joint angle. And that's going to be very simple. And if the axes are well selected, you will end up with just one transformation. So we are going to take the origins, as you suggested. And this origin has to, again, make use of the information we just displayed with those parameters. What is unique about those parameters? Well, we said we are using the common normal. This point of intersection with the common normal is very important. So now we're going to take the origin of our frames at the intersection with the common normal. This is the frame that will be assigned along I-1, and this intersection point is very important. Where is the next important point? I know you cannot point because you don't have any pointer, but just try to describe it to me. Yeah?
Somewhere along the x-axis?
Oh, no. I said this is the first origin of this frame. Now there is another frame here for the next joint. Where the origin is going to be? And here? Here? Higher? Okay. At the intersection of the common normal with this point. Wow. Right on. Okay. If you understand this, yeah, well, it is, but it's very important. I mean, sometimes if you select it down there, you run into a lot of other problems. You're not using the DI parameter properly, and everything becomes. So, okay, we take the intersection of the common normal with each of the axes and pick that point as the origin. Simple? You remember that? Okay. Then we take the z-axis to be along the joint axis. That's also simple. So zi-1 will be defined along axis I-1. And the other one obviously is here. Okay? Good. So what is left to define the frame? X-axis. So what do we do with the x-axis? So we know the origin, and we're going to say the x-axis has to be somehow orthogonal to z, and you are proposing to take this orthogonal to be along A-1 because this axis A-1 is orthogonal to z. I-1 because it is the axis orthogonal to the joint angle. So we take it in this direction. I think our problem is solved now because we assign, we pick the origin, we pick the z, we pick the x, the y is defined in the right-hand rule. So in this case, where is y? Y-1, it is inside the plane, right? X, y, z, right? You know this rule like this. Okay. You have to use your hand, otherwise you... If you end up with the opposite frame, all your transformation is going to be, well, wrong. Okay, good. And xi is along there. Now, we need to verify that we can go from zi minus 1 to zi using these 4 parameters. Do you think this is possible? So we have 2 frames. We assign 2 frames, and we should be able to describe this frame with respect to this, that is the homogeneous transformation, uniquely using those parameters. And we will do it just shortly, but there is no problem. We should be able to do it. Okay. This simple well, illustration of the frame assignment is much more complicated because there are all these special cases where you have intersecting axes, you have parallel axes, and you have that last frame that is still not defined. So you have to see where to define it, and you have freedom that is added, and you have to make your selection. And that's why the convention of always reducing, getting 0 parameters. So when you're doing the assignment, you're going to run into a lot of special cases. Hopefully, we will span them in your homework, midterm, and finals, so you will be mastering that problem. All right. So always remember this right-hand rule. It's very important, and try to practice with it if you're not familiar with it. Okay, so the summary for the frame attachment is the following. Is we pick the normals, okay? So you have the axis, you pick the normals, take the intersection and pick the origins. Along the origins you place your axis, and then you define the x-axis along the common normals. And that's it. So you have these 4 steps: finding the normals, the common normals, finding the origin at their intersection, taking the z-axis along the joint axis from the point of the origins you selected, and then placing the x-axis. Okay, now here is the x-axis which are placed from the intersection point toward the next link. So let's see the case of intersecting joint axis, which happens very often in the beginning and the end of the mechanism. In the beginning, usually joint 1 and 2 are intersecting, and joint 4, 5, and 6 are intersecting. I mean, in 6 degree of freedom manipulators, because we use wrist with the 3 intersecting joints, the mechanics of that is well understood, and it's quite easy to build. And also there are a lot of advantages in terms of the workspace and the freedom, except they have problems with respect to singularities, as we will see later when we study the Jacobian. But essentially, we're going to run into this case. So we know this point, and what we said is that, well, we picked the intersection, we picked the origin, and now this is the origin for frame I, and we place the z-axis, but the question is, where do you select your x direction? And that defines your, so if you place your xi in this direction, your angle, twist angle, will be measured about that. So it will be in this sense, in this direction. And if you place it in the opposite direction, so this is one direction. If you place it there, you get a different definition of your alpha I. And that is fine, because whatever you do, you have this freedom. Once you place xi, you define your alpha, and you are going to carry that transformation through the propagation, and this will be captured in your in your homogeneous transformation, and because you are going to find the next transformation between xi to the next one, everything will work out. So that freedom will be accounted for. You can come up with a description that use the minus sign or the plus sign, and that will work out with the next joint. The next joint will account for it, and everything will work out. You had a question? Okay. So this direction and the sign of alpha depends on your picking of x. So here is an example of the first link. I'm taking a revolute link. What we would like to do for a revolute link, if the first joint is revolute, like in the case of the Puma, what you would like to do is to almost say that the fixed frame and the moving frame are identical when theta is equal to 0. So you are really setting A alpha to be 0 and D1 equal to 0 for the revolute joint, and the only variable is theta, and the 0 of theta is when the two frames are identical. And that gives you the simplest form. So as you rotate about this joint, you are measuring theta from 0 to the value of theta. Okay? For a prismatic joint, what you are saying is, I'm going to take the two frames to be identical. This is imposed. This is your selection of the base frame. And you are placing the frame so that when these two are identical, D1, the prismatic joint, so you have a translation up and down, measured by this variable. And when D1 is equal to 0, you have the two frame coincident. So this is the frame 0 and the frame 1 are identical when D1 equal to 0. Your variable is equal to 0. All right? For the last link, if we have a revolute link, we are going to select the frame so that dn equal to 0, which depends on the following frame. That is, we are saying dn equal to 0, and that frame just measure the angle theta n, and when theta n equal to 0, basically we have xn and n minus 1 and xn aligned. Theta measures this angle between the x-axis, basically, as you rotate. And for the prismatic joint, we do the same thing to set theta n to 0. That is, we have, when dn equal to 0, xn comes down to be aligned with xn minus 1. So these are the conventions that you are going to try to enforce in your frame assignment. And using these, you will end up with the simplest form of the forward kinematics. But then, as I said again, the tool frame that you will add one more frame that will account for your task. And what is nice is once you have all this relation between the base frame and the end frame, all the other transformations are constant. That is, the next transformation will only involve constant parameters. So it is a very simple transformation. Okay, let's see the total summary now. So what we said is we need to introduce for each joint, we need to introduce these 4 parameters, ai, alpha I, theta I, and di. And what ai is doing, ai is measuring the distance between frame zi and between axis zi and axis zi plus 1 along the xi axis. Alpha I measures the angle between axis zi and axis zi plus 1 about the xi axis in the right-hand sense. di measures the distance between the x-axis, xi minus 1, and xi along the zi axis. And theta I measures the angle between the x-axis about zi. Now, this summary is very, very useful. Make a copy of this and keep it next to you. You're going to be confused about the eyes you are using and about the definition of these. Make sure that you have a copy of those definitions, not far away, and you will see that this is very useful. So, in these definitions, we have two distances and two angles. A and D are distances. A measure distances between the z-axis. D measure distances between the x-axis along the opposite axis. Okay? Alpha and theta measure angles between the z-axis and the x-axis about the other axis. Now, what is important is to notice the fact that we're looking at zi I plus 1, and here we're looking at xi minus 1 xi for the di. So be careful with which I we're talking about. Okay? You're confused enough to make a copy of it, right? Yeah, keep a copy. I think it is really useful. All right. So let's take an example. Very simple example. I'm going to take a planar robot, and this planar robot is just a set of 3 revolute joints. So we are talking about theta 1, theta 2, and theta 3. So where are the joint axes? Someone made a sign. I think I understood, but everyone. Do you see the joint axes? So the joint axes are coming perpendicular to the plane. Okay. So how do we pick the origins? In order to pick the origin, so you see 3 parallel axes. So how do we pick the origins? What do you need to do? You need the common normals, right? So you have between 2 parallel axes many possible common normals, but because this is in the plane, we are going to use the common normals in that plane, which is the plane of this screen. So where are the common normals? From this axis to the next one to the next one. Do you see it? Basically, this is the first common normal, the second common normal, and if there was a frame there, that will be along. So you know the common normals directly from here. So if you have the common normal are intersecting at this point. So the common normal is intersecting here, intersecting there, there, and this will become the origin of those frames that we are going to assign. So for frame frame 1, the common normal is intersecting here. The Z1 will be out of the page. X1 is along the common normal, and Y1 complete the direct frame. So basically you have this as the first frame, right? Any question about this one? Oh, very simple. Okay, do you agree with this second one? X2 is along the common normal, and Z2 is coming out of the plane, and Y2 complete the frame. And we are placing the lost frame, we have the Z3, and we are placing the origin. So X3 is taking along the direction perpendicular to the Z-axis and along the direction to L3, and that measures the angle theta 3. So between these frames, the only variables that you're going to see is theta 1, theta 2, theta 3, and now you need to introduce the first frame. So for the first frame, we said we are going to simplify. We are not going to select a Z0 out, in an arbitrary direction. We select Z0 along Z1. So this way, we will select the X0 to be coincident with X1 when theta 1 is equal to 0. And theta 1 is measured from here. So X0 will be along this direction. It's too simple. All right. So with this frame assignment, what we're going to have is the following. We defined for each of the joint those parameters, and now we have to identify those parameters and make sure for 1, 2, 3, 4, 6, whatever number of degrees of freedom, step by step, we are writing down these parameters. So we form a table, and this table is like this. You have alpha I minus 1, AI minus 1 that describe the links, DI and theta I that describe the connection of this link with the next one, and we say joint I 1. So for joint I, alpha 0 is equal to 0. There is no angle between Z0 and Z1. No distance, no distance between the two, it's 0. No offset, the 0, and the only variable is theta 1. So we're going to go through this one by one, and because of the fact that in this case the only variables that are going to be introduced are due to L1, L2. So L1 measures what? Which variable is measured by L1? The A. And that means A1 is going to be L1, and A2 is going to be L2. And basically now we have the description and the connection of each of the joints. So we build this table. Now, you have to notice something very important is that alpha, we set the value of alpha, 0. A, we set the value. These are constant. D, in this case, it's revolute joints, so we set the values. But for theta, I didn't go and measure. This is 32 degrees, and put theta 1, replace it with 32 degrees. Because this is going to move. So in this table, I'm setting the variable. If the second joint was a prismatic joint, the D will not appear as a 0, but it will appear as a variable. So theta or D will be a variable, depending on the type of the joint. Usually we add one more column. The column where we say configuration shown. In the configuration shown, you set the value of the variable. So theta 1 in the configuration shown is equal 32 degrees. You put 32 degrees in that column if needed. And sometimes we ask you to measure that variable. So, but now with those 4 parameters and this table, we should be able to describe the forward kinematics. That is, we should be able to describe the position and orientation of the end effector. Yes?
How do you get the position of the end effector if L3 isn't
Yeah, right now I'm going to frame 3. Now the transformation from frame 3 to that point, that blue point, involves another transformation, and sometimes we assign a frame 4 and we put 4 here, and then you can find that transformation. But for now we are just looking at the wrist point. This is the wrist point, and the variable is already in the wrist point. The only thing is a translation that is constant. Okay, we're ready. We're going now to find the transformation between 2 frames, and once we found one transformation using these parameters, we will generalize it, and we will multiply out all the transformations and find the forward kinematics. Okay, I see everyone ready. Let's go. So here is frame I, and I'm going to compute the transformation from I minus 1 to frame I. And we have these 4 parameters. And you're going to help me to do it. We need 4 transformations, 4 parameters. I'm going to use, I mean, I can't do it directly, but I'm going to use 4 transformations. I will do one at a time. So I think about di as an operator. And now if I use this di as an operator, I basically slide frame I to some other frame that just use this transformation from here to here. So this will be a frame here. Then I rotate this frame by theta, then slide it by A, and then tilt it by alpha. And I have 4 transformations, 4 simple transformations that will give me the total transformation. Do you agree? Very easy. So let's do it. So first transformation, I'm going to call this transformation that takes me from I down to P, ZP, and then we introduce ZQ, rotating to this, and then we go here to ZR, and then we tilt ZR to ZI minus 1. So basically, the way we're going to do it, we will move from this frame to this frame to this frame Q to this frame and slide it up and reach this one. And the transformation between each of them involves only one operator. So what is the operator between ZI and ZP? You remember those operators that I think we called Q, I think Q of the vector. So this Q is along the z-axis with a distance di. The second one is a rotation about the z-axis with an angle theta. The next one is a translation about the x-axis. The next one is a rotation about the x-axis, and that will lead us to. So if I find the transformation from I to P, P to Q, Q to R, R to I minus 1, then the total transformation between my transformation, and this is the most important thing you have. Once you have this expressed in terms of the A, D's, alphas, and thetas, then you have a general transformation that you can use in all your frames, and then you can build your forward kinematics. So this one, as I said, is a translation about the z-axis with di. This one is a rotation about the z-axis with theta I. This one is a translation about along the x-axis with a minus 1. And this one is a rotation about the x-axis with alpha I minus 1. Just multiply them out, you get your transformation, and we're done. And this transformation is simply this. So you have the answer. You don't have to do it. Well, I have the answer. Look, I to I minus 1 is given as a function of ai minus 1, alpha I minus 1, di, and theta. That's it. So we have this homogeneous transformation between this first frame and that final frame, And now we can apply it once we have these parameters. That is, once we form this table, we apply this transformation. We know those parameters. We have the homogeneous transformation. Correct? Once you have one of those transformations, you can go and multiply transformation between frames. You start from frame n and you go all the way to frame 0. And you have your transformation, homogeneous transformation from n to 0, which is now function of the parameters that are constant of the links, the a's and alphas and d or thetas, and the variables d or thetas. And with that, you have this information about the position of the end effector, which is contained in this transformation, the lost vector. Remember, the lost vector of this transformation contains x, y, and z. And the rotation matrix in this transformation contains the orientation of the frame with respect to the first frame. So you have your forward kinematics. Great. Do we have a homework today? Okay, so you're going to we have something about frame assignment. Good. So you're going to have fun this weekend. All right. See you next Monday.